Space, right? It's just wild. So many things we're still figuring out. Like today, we're diving into Einstein rings. I mean, just imagine a whole galaxy warped into like a perfect circle.
Yeah, pretty mind-blowing stuff.
Definitely not something you see every day.
And the thing is, it's not just a pretty picture.
Right. It tells us about the universe. Like we've got new data from the Euclid Telescope, the European space agencies
Oh yeah, Euclid's been doing some great work.
captured one of the most complete Einstein rings like ever.
It really is amazing what they've managed to capture. And it's a window, into stuff like dark matter, the early universe, big mysteries.
Okay, so before we get ahead of ourselves, what exactly is an Einstein ring? I always hear that bowling ball on a trampoline analogy, but I'm not sure I totally get it.
All right, so let's refine that analogy a bit. Picture that bowling ball, right, making a dip in the fabric. Now, instead of rolling a marble, think about shining a light past it.
Okay, I'm following so far.
That light's going to bend, going through that warped space. And that's basically what's happening with an Einstein ring, just on a cosmic scale.
So, like, instead of a bowling ball, it's a whole galaxy cluster.
Exactly. It's bending the light from a more distant galaxy that's behind it.
So the massive object is acting as a giant lens.
You got it. And when everything lines up perfectly, us, the lensing galaxy, the distant source, that light gets smeared out into a ring.
The Einstein ring.
Yep, and it's visual proof, right, for Einstein's theory of general relativity.
Which he figured out, what, over 100 years ago?
Yeah, way back in 1916. And it's still holding up.
It's incredible how his theories are still being validated. But this isn't the first time we've seen these rings, right?
No, not at all. Hubble, the Sloan Digital Sky Survey, even James Webb, they've all observed gravitational lensing, arcs, multiple images, all sorts of cool stuff.
So what makes the Euclid image so special?
The completeness, the symmetry, it's one of the most well-defined rings we've got.
It's not just about the aesthetics, though, right?
Definitely not. This ring tells us about something we can't even see, dark matter.
Right, because dark matter doesn't interact with light.
Yeah, we can't observe it directly, but it has mass, so it has gravity.
So we know it's there, just can't see it.
Exactly. And that's where Einstein rings become so useful.
How so?
They're like a cosmic scale. We can actually weigh the dark matter in that lensing galaxy.
Hold on, weigh something we can't see. What are we actually measuring then?
The distortion. The more massive the galaxy and its dark matter halo, the stronger it warps spacetime. The light bends more dramatically. So by looking at the ring's shape and how bright it is,
We can figure out how much dark matter there is and where it is.
that's the idea.
It's like looking at a shadow and figuring out the shape of the object.
Brilliant analogy.
We're using what we can see to map what we can't.
Right, and it's not just mapping. We can learn about the nature of dark matter itself, which is still one of the biggest mysteries in physics.
All right, now you've got me really hooked. Seeing invisible matter, confirming Einstein's theory, and this is just the beginning. So tell me more about this dark matter mystery. What are the top theories about what it could be?
Well, we've got a whole bunch of candidates, each weirder than the last. It's like a particle zoo out there.
A particle zoo. Okay, now I'm really interested. Let's take a look.
All right, so first up, we've got WIMP's weakly interacting massive particles.
Sounds kind of ominous.
They're massive, which fits what we see in the universe, but weakly interacting, so they don't mess with light much.
Hence the invisible part.
Exactly. Makes them tough to detect directly.
So like cosmic ghosts, passing through walls, only leaving their gravity behind.
You're getting the picture. And for a while, WIMPs were the top contender.
But you said something about them losing traction.
Yeah, we've been searching for decades with super sensitive detectors and nothing concrete yet.
So they're not ruled out, but the search continues. What else is in this particle zoo?
Well, we've got axions, much lighter than WIMPs, even weaker interactions.
Even more elusive. How do we even look for something like that?
It's tricky, but there are experiments using strong magnetic fields, trying to make them show themselves.
If we find them, that's a big deal, right?
Huge for particle physics and dark matter.
WIMPs, axions, it's like the universe is playing hide and seek. Anything else?
How about sterile neutrinos? These are like the ghostlier cousins of regular neutrinos.
Which are already hard to detect, right? I've heard they go through miles of lead like it's nothing.
Yep. And sterile neutrinos, even less interaction with normal matter.
So we're talking about, what, practically invisible particles making up most of the universe's mass.
It's a humbling thought, shows how much we still don't know.
Speaking of humbling, you mentioned primordial black holes. That sounds straight out of science fiction.
I know, right? But the early universe was crazy dense, super energetic.
So these aren't the supermassive black holes we hear about eating stars and stuff.
Nah, these would be tiny, maybe even microscopic. But if enough formed way back then,
They could be the dark matter.
it's a possibility. Shows how diverse the explanations can get.
This particle zoo is wilder than I imagined, but let's zoom out for a sec. We've got these elusive particles maybe holding the universe together. We've got this mysterious dark energy making it expand faster. It's a lot to process.
It really is. But that's the beauty of science. Pushing the boundaries, finding new stuff, constantly challenging what we think we know.
You said before that Einstein rings are more than pretty pictures, they're tools. How do we actually use them to study all this?
Remember how we talked about them being like a cosmic scale? Well, we can map out dark matter around a galaxy by looking at how distorted the ring is.
Right, but it's not just about where it is, but what it is.
Exactly. Each of those dark matter candidates, WIMPs, axions, the whole zoo, they'd each distort the ring slightly differently.
So by looking at lots of Einstein rings really closely,
We can start to rule some candidates out.
each ring is a clue, basically.
And with Euclid out there scanning the sky, we're getting tons of clues. It's a golden age for this kind of research.
So we're like cosmic detectives using these rings to solve the universe's biggest mysteries.
I like that. And the more we learn about dark matter, the better we understand how galaxies form, how the universe itself evolved.
Okay, we also talked about how this Einstein ring gives us a peek into the early universe. How does that work?
Think about it. Light has a speed limit. When we look at something far away, we're seeing it as it was, not as it is right now.
So farther away equals further back in time.
Right. And this lens galaxy, its light has been traveling for billions of years.
A snapshot of the early universe, like a cosmic time machine.
Exactly. And the lensing effect makes it even better. It amplifies the light so we can see more detail.
It's incredible how much info we can get from a single beam of light. Like we're deciphering an ancient language written in like the fabric of the cosmos or something.
That's a beautiful way to put it. And each new Einstein ring we find is like adding another chapter to that story.
We're building a more complete history of the universe.
Exactly. And the more we find, the more awe-inspiring that story becomes.
Okay, so we've gone from invisible particles to ancient starlight here. But for someone who isn't, a cosmologist or whatever, why should they care about any of this?
It's a great question. I think at its core, this is about understanding our place in the universe, where we come from, how it all works, what our future might be.
So not just curiosity, but a bigger picture kind of thing.
Yes. Plus, along the way, we're making new technologies, pushing what humans can do.
Inspiring new generations of scientists, right?
Absolutely.
When I first heard about Einstein rings, I just thought they looked cool. But now I'm realizing it's so much more than that. It's about exploring those fundamental mysteries that humans have been asking about forever.
It's a journey, outward into rays, but also inward, into our own curiosity.
And that journey's not over. We've got more to uncover about Einstein rings and what they can tell us. In the next part of our deep dive, we'll look at how all this research is changing our understanding of the universe's evolution and what exciting new discoveries are just around the corner. Okay, so last time we were talking about dark matter. We left off on kind of a cliffhanger.
A particle zoo, as I recall. Lots of candidates, each with their own quirks.
Right, and you mentioned dark energy too, but maybe we can circle back to that later. First, I want to hear more about these dark matter contenders.
Sure, happy to dive back into the particle zoo.
So remind me, where did we leave off?
We were just starting to explore some of the possibilities.
Right, WIMPs, axions. It's all a bit mind-boggling.
It is, isn't it? The universe loves to keep us guessing.
So let's start with those WIMPs again. Weakly interacting massive particles, was it?
Yep, that's them. They're thought to be massive, which would explain their gravitational influence. But they interact very weakly with normal matter and light, making them difficult to detect.
Hence the weakly interacting part, I guess.
Precisely. And that's why they've been so elusive for so long.
But you said they were losing traction.
Well, we've been looking for them for a long time with no definitive evidence. It's possible that they're just much rarer than we initially thought, or maybe they don't exist at all, and dark matter is something else entirely.
So the mystery continues. What about those other candidates?
Axions.
Yes, those.
Axions are fascinating. They're much lighter than WIMPs and interact even more equally with matter. Think of them as even ghostlier versions of WIMPs.
How do we even begin to look for something so elusive?
It's a challenge, but scientists are developing some incredibly clever experiments. They're using powerful magnetic fields to try to coax axions into interacting, hoping to catch a glimpse of them.
So it's a bit like setting a trap, but for something we can't even see.
You could say that. If we do manage to detect them, it would be a monumental discovery.
Okay, so we've got the heavyweights, the WIMPs, and the lightweight contenders, the axions. What else is in this cosmic lineup?
Well, there are also sterile neutrinos. Now, regular neutrinos are already incredibly difficult to detect. They can pass through miles of lead without a trace.
Yeah, I've heard about those. They're like tiny, almost massless particles that just zip through everything.
Exactly. Sterile neutrinos are even more elusive. They're hypothetical particles that interact even less with normal matter.
So we're talking about particles that are practically invisible, potentially making up a huge chunk of the universe's mass.
It's a mind-bending thought, isn't it? And it really highlights how much we still don't know about the fundamental building blocks of our universe.
It's almost like trying to describe something that's beyond our comprehension.
In a way it is, but that's what makes it so exciting. We're pushing the boundaries of human understanding, trying to grasp concepts that are completely alien to our everyday experience.
And speaking of alien concepts, what about those primordial black holes you mentioned? That sounds like something straight out of a science fiction movie.
I know, right? But it's a fascinating idea. You see, the early universe was an incredibly extreme environment, super dense and energetic.
Well, we're not talking about the supermassive black holes that we usually hear about, the ones gobbling up stars and galaxies.
No, these would be much, much smaller, perhaps even microscopic. But if enough of them formed in the early universe, they could potentially account for the missing mass we attribute to dark matter.
So instead of a handful of giant black holes, we could have a universe teeming with tiny ones. That's a pretty wild thought.
It is, and it just goes to show that we have to keep an open mind when it comes to explaining dark matter. The answer could be something we haven't even thought of yet.
This whole particle zoo is wilder than I ever imagined. But let's take a step back for a moment. We've got these elusive particles potentially holding the universe together. We've got dark energy pushing it apart. It's a lot to process.
It really is. But it's also a testament to the power of human curiosity and our drive to understand the universe around us.
You mentioned that Einstein rings are more than just pretty pictures. They're tools for unlocking these mysteries. How do we use them to study dark matter and the early universe?
Well, remember how we talked about them acting like a cosmic scale? By carefully analyzing how much an Einstein ring is distorted, we can map the distribution of dark matter around the lensing galaxy.
Right, but it's not just about finding out where dark matter is, but also what it's made of.
Exactly. Also, these candidates, WIMPs, axions, sterile neutrinos, primordial black holes, would create a slightly different lensing signature.
So by studying a large number of Einstein rings in detail, we can start to narrow down the possibilities.
Precisely. And with powerful telescopes like Euclid scanning the skies, we're entering a new era of discovery. The data they collect will help us unlock the secrets of dark matter and shed light on the early universe.
It's like we're cosmic detectives, using these rings to piece together the universe's grand puzzle.
I love that analogy. And the more pieces we find, the more we understand about how everything came to be.
So we've got dark matter setting the stage, galaxies evolving over time. Where does dark energy fit into all of this?
Ah, yes, dark energy, the ultimate cosmic mystery. This mysterious force is causing the universe's expansion to accelerate.
So while dark matter pulls things together, dark energy pushes them apart.
Exactly. It's a cosmic tug-of-war playing out on the grandest of scales.
And we have no idea what it is.
Not really. It's one of the biggest unsolved mysteries in physics.
So we have all these possibilities for dark matter WIMPs, axions, sterile neutrinos, primordial black holes. Are there any frontrunners for explaining dark energy?
One of the leading contenders is the idea that dark energy is a property of space-time itself, a kind of cosmological constant that Einstein first proposed.
Wait, so empty space has energy. That seems counterintuitive.
I know, right? But it's the simplest explanation that fits the current data.
It's all incredibly mind-blowing. Invisible matter, a mysterious energy pushing the universe apart, and the possibility of rewriting the laws of gravity. It feels like we're on the verge of some major scientific breakthroughs.
I agree, and that's what makes this such an exciting time to be studying the universe. With all these powerful new tools at our disposal, we're poised to make some incredible discoveries in the coming years.
So we're using these cosmic lenses, these Einstein rings, to decipher the universe's deepest secrets.
We are. It's like we're reading the universe's diary, trying to understand its history and its ultimate fate.
You know, it's amazing to think that we started by simply admiring the beauty of Einstein rings. Now we're using them to probe the fundamental mysteries of the universe.
And that's just the beginning. There's so much more to learn. We need to keep asking questions, keep exploring, keep pushing the boundaries of what we know.
Well said. And that brings us to the end of another fascinating deep dive into the mysteries of the cosmos. We've explored dark matter, dark energy, and the incredible power of gravitational lensing. I hope you'll join us next time as we delve even deeper into the universe and explore the cutting-edge research that's shaping our understanding of where we came from, where we're going, and what our place is in this vast and wondrous cosmos. Last time we were talking about all these wild ideas, invisible matter, a mysterious force pushing the universe apart. So how does all this research actually change what we know about how the universe evolved?
Well, think of it like a giant puzzle, right? Every Einstein ring we find, every new piece of data about dark matter, it helps us see the bigger picture, like how the universe began and how it's changed.
Okay, so we've got dark matter's gravity, but how does that fit into the whole evolution thing?
Dark matter, you see, it's like the scaffolding that galaxies are built on. Way back in the early universe, its gravity pulled together all this gas and dust. Those were like the seeds for the first stars and galaxies. Without dark matter, the universe would be a very different place.
It's crazy to think about. forces on such a massive scale.
It really is. And remember those lensed galaxies, the ones that let us look back in time?
Yeah, the ones that act like time machines.
Exactly. By studying them, we can actually see how galaxies have changed over billions of years, how they've grown, merged, and interacted with their surroundings.
So it's like watching a cosmic movie.
Yeah, but instead of frames, we're analyzing ancient light.
Okay, we've got dark matter bringing things together, galaxies changing over time. Where does dark energy come in?
Ah, yes, dark energy, the biggest enigma of them all.
I think you said it was making the universe expand faster.
That's right. It's like an anti-gravity pushing everything further and further apart.
So while dark matter pulls, dark energy pushes.
Precisely. It's a cosmic tug of war. And here's the kicker. Dark energy seems to make up most of the universe's energy.
Wow, that's a lot of energy, and we have no idea what it does.
Not really. It's one of the biggest mysteries in physics.
We talked about all those candidates for dark matter, like WIMPs and axions. Any leading theories about what dark energy might be?
Well, one of the top contenders is that it's a property of space-time itself, like a cosmological constant, which Einstein actually proposed way back when.
Wait, so empty space has energy?
It's a wild concept, I know, but it's the simplest explanation that fits what we see. Another possibility is that we need to rethink gravity, come up with a whole new theory.
It's a lot to take in: invisible matter, a mysterious energy, maybe rewriting gravity. It feels like we're on the edge of some huge discoveries.
Absolutely. And that's where telescopes like Euclid and all those next generation ones are so important. With better technology, we can gather more data, map dark matter better, study how galaxies change in more detail.
So we're using these Einstein rings not just to look at the universe, but to really understand it.
Exactly. It's like we're trying to read the universe's diary, figure out where it came from and where it's going.
It's amazing to think we started by just being like, whoa, cool rings. And now we're using them to solve these huge mysteries.
It's a testament to human curiosity, our need to explore and understand.
This has been an incredible journey. We've learned about the mind-bending physics of Einstein rings, the mystery of dark matter, and how all of this shapes our understanding of the universe.
It's been a pleasure sharing this journey with you.
So to all our listeners out there, keep looking up at the sky, keep asking those big questions, never lose your curiosity. This has been The Deep Dive. Thanks for joining us.